Hi everyone. Today we're starting a new chapter, chapter 17, and in this chapter we're going to focus a little more on aqueous ionic equilibrium. So we're going to use some of the concepts that we saw in chapter 16, but this time we're going to apply it in different ways. And the first thing that we're going to go over are buffer solutions. So a buffer resists changes in pH by neutralizing added acid or added base. And buffers are really useful for many different applications. When I was doing research, we tried to keep the pH of our solutions around the same pH as animals and humans. So in humans, our pH is around 7.4, and you can create a solution that will maintain a pH of about 7.4. So that's really great if you need to mimic, a human system in your experiment. So buffers contain either significant amounts of a weak acid and its conjugate base, or it contains significant amounts of a weak base and its conjugate acid. So again, for instance, blood has a pH of about 7.4, and that's due to different ions and molecules in our system. So for instance, blood has a mixture of carbonic acid and its conjugate base, which is bicarbonate. So let's look at a real-world example of why buffers are important. Now, if you've ever used antifreeze, antifreeze often contains a molecule called ethylene glycol. And ethylene glycol tastes really sweet, so it attracts pets or other wildlife, and they really want to consume it because it tastes so good. Now, ethylene glycol is a type of alcohol. So initially, if someone has consumed ethylene glycol, they'll act sort of drunk. And then ethylene glycol will be metabolized in the liver to something called glycolic acid. So down below we have the structure of ethylene glycol. And you'll notice that there are two of these OH groups, and that indicates that we have an alcohol. So there's two of them present. And then when ethylene glycol is metabolized, so it's broken down in the liver, it turns into glycolic acid. So instead of this CH2 group here, we end up with a CO group. So this would look kind of like this. So we would have a carbon double bonded to oxygen instead of two hydrogens. Now, glycolic acid is really the problem. If you have a high enough concentration of glycolic acid in your bloodstream, that overwhelms the buffering ability of the blood. And so that's going to cause your blood pH to drop. So your blood is going to become more acidic. Now, what that has an effect on are your oxygen levels. So down below we have a reaction between hemoglobin and oxygen. So hemoglobin is what carries oxygen through our system. And in the process of combining with oxygen, hemoglobin will release a proton or hydrogen ion. Now remember from Le Chatelier's principle, if you add a lot of product to a solution, that's going to shift equilibrium to the left or towards the reactants. So if we add more acid to our solution, we're essentially adding more H+, which is going to shift the system back towards hemoglobin and oxygen as separate entities. So the more acid you have in your system, the less likely hemoglobin is to carry oxygen through your blood, which is really bad for us because we need oxygen to survive. Now, luckily, there is a treatment for this, for glycolic acid here. One treatment is to give the patient ethyl alcohol, which is ethanol. So ethanol is in alcoholic beverages, and it has a higher affinity for that enzyme that metabolizes ethylene glycol. And so if the enzyme prefers to attach to ethyl alcohol, that will prevent ethylene glycol from turning into glycolic acid. And so then the pH of the blood should stay relatively the same, and hemoglobin can carry oxygen through the blood. So buffers are very important, but they do have a limit. So if you do add too much acid or too much base to a buffer, the pH can change, unfortunately. But let's talk a little bit more about how to make a buffer. So here we have an acidic buffer solution. And in an acidic buffer solution, we need significant amounts of both a weak acid and its conjugate base. So here we have an example of acetic acid, which is a weak acid. And this is what's present in vinegar. And then we're also going to add significant amounts of its conjugate base, which is acetate. And then just to balance that negative charge, we also have a sodium ion. Okay, so once we mix these two together, we'll have a solution that contains both acetate, acetic acid, and then some hydronium ions and sodium ions. And the hydronium ions are coming from the acetic acid and its interaction with water. So now, what if we add a strong base to our buffer solution? It's going to be neutralized by the weak acid. So down below we have our strong base, sodium hydroxide. And again, when it's added to solution, it will interact with the acid. Now remember that a base is a hydrogen acceptor and an acid is a hydrogen donor. So the hydroxide from our strong base is going to grab onto a hydrogen from the acid, and we form a water molecule. And then whatever's left over is just going to remain floating in solution. So in this case, we have sodium and acetate left over. And we can write that as a molecule, but it is aqueous. So just remember that those ions are actually separate and they're floating around. Now, if the amount of strong base added to solution is less than the amount of acetic acid present, then the pH change will be pretty small. So we'll maintain that same pH level that we're trying to stick with. But if we add way more base, then that's going to overwhelm the system and the pH change will be greater. So buffer solutions do have a capacity, and we'll talk more about that later. Now, what if we add a strong acid to our buffer solution? So let's say that we add a strong acid, like hydrochloric acid. That is going to interact with the conjugate base from the buffer. Now, remember again that acids donate hydrogen ions and bases accept them. So in this case, the acetate ion is our base, and we're going to see that it takes a hydrogen from the acid, and we end up with acetic acid. And then our other product is whatever's left over, which in this case is sodium chloride. But remember that this is aqueous, so really we have a sodium ion and a chloride ion floating around in solution. Now, if the amount of hydrochloric acid is less than the amount of conjugate base present, the pH change is small. So we should maintain something relatively close to the pH we're trying to maintain. So let's calculate the pH of a buffer solution that is 0.1 molar in acetic acid and 0.1 molar in sodium acetate. Okay, now this example is in your textbook, but let's go over it together. So first, I'm going to write out the reaction of acetic acid with water. Now again, this is a weak acid, so when it interacts with water, we do have a reverse reaction from our products. So in this reaction, water is acting as a base, so it's going to grab onto a hydrogen ion and form the hydronium ion. And then our other product is the acetate ion. All right, so now we're going to use this as our guide for determining the changes in concentration, and this will help us set up our ice table. Okay, now usually we're given the concentration of our reactant and we're not told the concentration of the products. But in this case, we have both some amount of our reactant and our product initially. So we're told that we have 0.1 moles per liter of acetic acid, and then we also have 0.1 moles per liter of acetate present in solution. So that's coming from this here, the 0.1 molar sodium acetate. And then we always say we have approximately 0 hydronium ions because there is some amount coming from the autoionization of water, but it is negligible. So we say we have approximately 0 hydronium ions. All right, so now let's figure out the change here. Everything is in a 1-to-1 ratio, so we don't have to worry about stoichiometry. So we are going to lose some amount of our acid, and we're going to gain some amount of our products. And again, this is for the interaction of the acid with water. Now our equilibrium expression for the reactant is 0.1 minus x. And then for the hydronium ion, it's x. And for the acetate ion, it's 0.1 plus x. Okay, now our next step is to write out the acid ionization constant expression. And then we'll plug in these values here, or these expressions. So as always, we have products over reactants. Now, we do need the acid ionization constant for acetic acid. And if we look in the back of our textbook, it tells us that the acid ionization constant is 1.8 times 10 to the negative fifth. And then we'll plug in our equilibrium expressions for each of these concentrations. So the hydronium ion was x, the acetate ion was 0.1 plus x, and we'll divide that by 0.1 minus x. Now, let's assume that x is small. So we're going to ignore these changes in x because they shouldn't be very significant, especially because the Ka value is very small. Okay, so now that gives us 1.8 times 10 to the negative fifth. That's equal to x times 0.1 divided by 0.1. Okay, so now that kind of shows, well, we can just cancel 0.1. It's in the numerator and the denominator. And that means that x is equal to 1.8 times 10 to the negative fifth. So x is just equal to the acid ionization constant. Now, let's check and make sure that that is valid. So we're going to take our acid or our hydronium ion concentration at equilibrium, which is 1.8 times 10 to the negative fifth. And we're going to divide that by our initial acid concentration, which was 0.1, and then multiply that by 100. And we find that we should have a percentage of 0.018. So that is a valid assumption. We can, in this instance, say that the value of x is equal to the acid ionization constant. Now, our actual goal was to figure out the pH. So remember that x is also equal to the concentration of the hydronium ions. So when we're calculating the pH, we're going to take the negative log of that. I'm just going to box in our check there so it doesn't interfere with the rest of our work. And if you plug this into your calculator, you should get a value of 4.74. All right, so that is our pH for this buffer solution. And if we add a little bit of base to this buffer solution, it should maintain a pH of around 4.74. So maybe it will be a tiny bit higher, like 4.76, but that's still pretty close. And then if we add a little bit of acid, it will be neutralized by the conjugate base, and we should maintain a pH of about 4.74. So again, buffers are really, really useful if you need to create a certain acidic or basic or neutral environment, and you don't want outside forces messing that up. So again, just to reiterate, buffers work by applying Le Chatelier's principle to weak acid equilibrium. So again, buffer solutions contain significant amounts of the weak acid molecules, and these molecules react with added base to neutralize it. So if we have HA as our generic weak acid, it will react with any hydroxide ions to produce a conjugate base and conjugate acid. Okay, now if we add acid to our buffer, the buffer solution also contains significant amounts of the conjugate base. So the conjugate base will interact with added acid to make more acid. So if we have our conjugate base, it will react with any added acid to produce that weak acid that we originally had in solution. Okay. Now on Canvas, I posted the worksheet for chapter 17, and on problem 1, it says a buffer contains significant amounts of ammonia and ammonium chloride. Write equations showing how this buffer neutralizes added acid and added base. So if you want to try this problem on your own, feel free to pause the video, and then in a few minutes we'll go over that together. Okay, so we're told that this buffer contains significant amounts of ammonia, and you might remember that ammonia is NH3, and then we also have significant amounts of ammonium chloride, and that is NH4Cl. But remember that in solution, ammonium and chloride will actually be floating around. So ammonium is always soluble. So really, we have the ammonium ion and the chloride ion. So ammonia typically acts as a weak base, and ammonium acts as a weak acid. All right, so let's say we add acid to our buffer solution. Let's say we add hydrochloric acid. So one question to ask yourself then is, what will the strong acid interact with? Will it interact with ammonia or ammonium? So in this case, it will react with a base, so it's going to interact with NH3. All right, now because we have a weak base here, we are going to experience equilibrium. And the base, again, is going to accept a hydrogen. So we get back our ammonium ion. And then our other product is whatever's left over, which is the chloride ion. And then everything in this case is aqueous. Now what if we add a base? So let's say we add sodium hydroxide. what will that base interact with? Will it interact with ammonia or ammonium? So it should interact with ammonium, the weak acid, because it does want to grab onto a hydrogen. Okay, so we are going to have some equilibrium here because we do have a weak acid. And let's see. So the base is going to grab onto a hydrogen. And that's going to form water. And then what's left over is the sodium ion. Okay. So we'll stop there today, and we'll pick this up next time. So remember to work on your Chapter 17 homework on sapling if you feel comfortable with some of those early problems. You don't want to fall too far behind. And you can also read along in your textbook and try some of the blue problems at the end of the chapter. The blue problems have answers in the back of the book. All right, I will see you in the next video.